Hello, I'm John O'Doherty, and this is my final presentation for this paper that I've been implementing for the module Real-Time Rendering. It's called Real-Time Blur Simulation of Varifocal Spectral Lenses in Virtual Reality, and it was first presented in SIGGRAPH Asia 2022. So there's a few pieces of background material we need to go over before I can start discussing my implementation. I suppose there's theoretical aims and there's I suppose more practical aims of the paper. The main practical aim of the paper is to make a system where people can iterate more quickly on lens designs using VR, and whether that's varifocal, multifocal, or even upcoming autofocal designs using VR, because otherwise it can be a lengthy process to manufacture these lenses, and having good high quality simulations of them helps a lot. So the theoretical aim to achieve that is to create a shader that lets us simulate these lenses. So obviously lenses apply blurs, and blurs have been used in so many things across the years. Typically they're done as Gaussian blurs. However, when you're considering spectacle lenses, Gaussian blurs aren't really physically correct. So that's the main kind of theoretical aim of the paper, is to implement some more physically correct version of a blur than a Gaussian one. It's still a kernelized blur effect, but instead of using a Gaussian sort of formula, it uses an ellipse. So how that works is that we have these set of textures, and they define the major axis, the minor axis, and the rotational axis of the ellipse, and we basically put that in a kernel, and if a point is inside it, it's summed up. Otherwise it's not, and then we divide the results by the amount of points included. So the next slide is just an overview of the methods from the paper. Yeah, so this is kind of the overview of how they went about implementing this shader. So on the left we have our inputs, the rendered textures from Unity, as well as these three power map textures, which define the major axis, minor axis, and rotational axis of the ellipse, as I said before. So these power map textures are multiplied together with the depth buffer to give us this blurry ellipse. There's also a downsampling step in order to help improve performance, because sometimes these could be really large textures, and especially with VR headsets having high resolution performance, and having high resolution and requiring high performance, downsampling makes quite a lot of sense in this case. So then we take the downscale textures and our blurry ellipse textures, and we multiply them together to give us these foreground and background buffers. Or we do the kernel based ellipse function to take a look at these foreground and background buffers. So the reason we have a foreground and a background buffer is to, much like other effects, is to help prevent blur discontinuity, so things in the foreground can blur over things in the background, and not the other way around, which looks weird. There's also an interpolation into a final texture, just to get that resolution back. So in the next part I'm just going to show the demo in Unity. So this is the scene that I've been using to test out. It's a very simple scene. It's just a prefab called Mini Toon Office that I found on the asset store, but it provides a nice parallel to the original paper without being overly complex. So this effect is obviously a post-processing effect, so it doesn't really require much geometric complexity to show. It actually scales a lot better the intensity of the effect scales a lot better with the resolution. So I'm going to switch over to the game view now. I've got the game running. I don't have the effect on. So you can see here I'm rendering the game at 1440p widescreen. This is just what it looks like without the game on, just a simple fly camera around, usual stuff. So for the textures that I was talking about earlier, those power map textures, I had a lot of problems generating them. So I'll show you a few of the ways I tried to generate them. First off, just trying to do it for one axis, just to see Basically, the problem is that they show them, but they don't actually describe anything about those textures, sort of what's expected to be in them. They obtain them by laser scanning pre-existing lenses, which is obviously something I don't have access to as a computer science undergraduate computer science student. Um, it's not something I can do. So I was trying to recreate them as best as I could. Um, so this is kind of an exaggerated version of them, where I've set everything to 255, so you can see the green and the blue channels have different gradients on them, just to see what happens. Um, and this is what the ones that are actually used looks like. Uh, they're just very low pixel intensity values because the maths works out a little nicer. It should work out a little nicer. So it looks all black, but I promise it's not. So if I turn on the effect, you'll notice that there's not too much changed. This is due to these textures. They're just they just aren't correct. It's been something that's very hard to recreate. Um, but we can zoom in on the image and see that the shader does actually have an effect. So I'll take a look here. So if I turn it off again, we can see we are still getting some soft blurring effect. So aside from the technical evaluation of this method, we can talk about, or aside from the aesthetic evaluation of this method, we can talk about the technical evaluation, how long it takes to run, if does it hog up much resources. So this is a screenshot taken from the Unity profiler. It tells you everything you'd want to know about what's taken up time in your per frame. So in a frame that took 5.74 milliseconds to render, my script took 0.03 milliseconds to run, even with these different blitz. So it's quite performant, and that's at 1440p. So I'd be quite confident about putting it into a VR environment, one where high frame rate at high resolution is very important. I think my implementation would still function very well. So that's everything from me, and thanks for watching.